Welcome to the Deep Dive, the show where we distill complex information into sharp, actionable insight just for you.
Today, we're going back to the absolute foundations of chemistry.
We're talking about the S-block elements, Group 1, the alkali metals, and Group 2, the alkaline earth metals.
And these groups really are foundational.
Yeah.
They define almost every chemical rule you first learn.
They're sitting way over on the far left of the periodic table, right?
Exactly. Which makes them intensely electropositive. They are the ultimate electron donors. They practically can't wait to shed those outer electrons to get stable.
And that desire to shed electrons, that's really the whole story here, isn't it?
It is.
So our mission today is pretty simple. We want to quickly pull out the core chemical differences, find some of the unexpected applications that, run modern life, and really dig into the surprising exceptions.
The rule breakers.
Exactly, the elements that break the rules.
Okay, so to set the technical stage, Group 1 elements are NS11. They have that one single electron, which they lose very readily to form a monovalent M+ calcantation.
So an oxidation state of +1.
+1. And then Group 2, having NS22, they sacrifice 2 electrons to form M2+ collocations.
Oxidation state +2.
Correct.
But before we get too deep into the theory, let's start with a little bit of spectacle. The, I think, most memorable property of these elements is what happens when you heat them.
Oh, the flame colors. It's truly beautiful chemistry in action.
You're literally seeing the visible evidence of energy transfer.
You are. When you heat the salts of these metals, their valent electrons, they absorb that energy and they jump to higher orbits.
And when they fall back down,
They emit that energy back out as light at very, very specific frequencies.
and those colors are just immediate identifiers. You think of sodium, that unmistakable piercing yellow you see in streetlights.
Yeah.
Lithium gives off a deep, beautiful crimson red.
And Group 2 falls right along. Calcium gives you a distinct brick red flame.
Yeah.
And barium, a little further down, that gives you a striking apple green.
So they're not just pretty, they're diagnostic.
Crucial diagnostic tools, absolutely.
Okay, let's unpack Group 1 then. The alkali metals. The word alkali itself, it tells a story. It comes from the Arabic alquali.
That's right. Alkali, meaning
Yeah.
plant ashes, which is where we, historically source things like potassium carbonate.
And these elements, lithium, sodium, potassium, they're all ridiculously soft.
You could cut them with a butter knife. They have very low densities, low melting points.
And the reactivity, it just skyrockets as you go down the group, right?
Yeah. From lithium all the way to cesium.
That's the core trend. Reactivity goes up because the ionization enthalpy goes way down.
Meaning it's easier to pull that electron off.
Laughably easy. As the atoms get bigger, that single valence electron is folded from the nucleus. It's heavily shielded, just begging to leave. That's what makes them such powerful reducing agents. And speaking of reactivity, their reaction with oxygen is a perfect example of this nuance. You'd think they'd all just form simple oxides.
But they don't. And this is a huge distinction in the group, a really key point.
So what happens?
Now, the smallest one, lithium, it's the only one that actually forms a normal simple oxide, text O2.
Okay.
When you get to sodium, its preferred product is the peroxide, text O22.
Then it gets even weirder. Potassium, rubidium, cesium.
They go one step further. They form what we call superoxides, text MO22.
Superoxides. What's the big deal with that?
It's a huge shift. The normal oxides and the peroxides are usually colorless, diamagnetic, but superoxides, like potassium superoxide, they're yellow or orange, and crucially, they're paramagnetic.
So they have unpaired electrons.
Exactly. That change tells you just how fundamentally different the heavier alkaline metals are behaving.
No, we have to talk about the rebel of Group 1, lithium. It's like it!
Yeah.
Just didn't get the memo on how to be an alkali metal.
It definitely breaks the mold. And the reason is all about its size. Lithium is exceptionally small, which gives it a really high charge density, high polarizing power.
So it behaves differently. Physically, it's harder, higher melting point.
Right. And chemically, it does something the others just can't. It reacts directly with dinitrogen gas.
With nitrogen? But that's so inert.
Incredibly inert. But lithium's tiny, potent cation has enough polarizing power to actually activate that nitrogen molecule and react with it. It forms lithium nitride, text XDAT.
Wow. And that unique behavior creates this connection across the periodic table, right? The diagonal relationship.
To magnesium, yes.
Yeah.
The size and charge density of text X plus stellar make it chemically almost a twin of text 2 plus lovely.
What are the similarities?
They're striking. Both are harder metals. Both react really slowly with cold water. and their salts decompose the same way. Lithium carbonate and magnesium carbonate both break down with heat to form their oxides and textam-22.
So if you see lithium doing something strange...
Look to magnesium. You'll probably find the answer there.
Okay, let's shift over to group 2, the alkaline earth metals. Now they have 2 electrons to lose, which has to change things.
Oh, it changes everything. Because they lose 2 electrons, they get a higher net charge and much smaller ionic radii than their group 1 neighbors.
Which means in the real world.
They are significantly harder, denser, and have much higher melting points. They're generally less reactive than group 1, and their hydroxides are less basic.
You also mentioned they interact with water differently. They form more hydrates.
Much more.
Yeah.
Again, it comes down to that size and charge density. The smaller, more highly charged textam-2 plus gytrons have this massive electrical field.
So they just pull water molecules in.
They pull them in and hold on tight. That's why you see things like magnesium chloride as a hexahydrate, textavgClS6, textavAA. You just don't see that with simple sodium chloride.
But the weirdness doesn't stop with group 1. Beryllium, the smallest in group 2, is the ultimate outlier here.
Beryllium is a dramatic outlier. It's so small, its charge density is so high, that it basically refuses to form purely ionic compounds.
It prefers covalent bonds.
It favors a high degree of covalency. The other group 2 metals are mostly ionic. But beryllium chloride, textal-22, is actually a covalent compound. It exists as a polymeric chain.
That must mess with its solubility, right?
Completely. Because it's covalent, beryllium chloride is soluble in organic solvents. Totally against what you'd expect for a metal halide. It's so reluctant to be ionic that it doesn't even react with water.
Not even when it's hot.
Not even when you heat it to high temperatures.
And beryllium, just like lithium, it has its own diagonal twin.
Aluminum. That's the second key diagonal relationship you have to know.
So similar properties.
Very similar. Both beryllium chloride and aluminum chloride are soluble in organic solvents, and both are strong Lewis acids, meaning they are eager electron pair acceptors.
And what about their hydroxides?
Critically, their hydroxides are both amphoteric.
Meaning they react with both acids and bases.
Yes. Most group 2 hydroxides are strong bases, but beryllium hydroxide and aluminum hydroxide can react with both, dissolving in either extreme. It's a huge chemical commonality, all driven by that similar charge-to-size ratio.
Okay, so we've got the rules and the fascinating rule breakers. Now let's connect this to real life. These elements are absolutely fundamental to, well, everything. Tech, biology.
Industrially, they are indispensable. Lithium. I mean, the modern world runs on lithium. It's the lightest metal. It offers the highest power-to-weight ratio.
Which is why it's the backbone of every rechargeable battery. Your phone, your car.
All of it. And then there's beryllium. We said it was light with a high melting point. That makes it perfect for X-ray technology. It's used for radiation windows because it has very low X-ray absorption.
The particles can just pass right through.
With minimal interference. And then we use liquid sodium metal as a coolant in fast breeder nuclear reactors.
Liquid metal. That sounds dangerous.
It sounds strange, but it has exceptional thermal conductivity, and it can operate at extremely high temperatures without needing high-pressure systems like water does.
And shifting to life itself, 4 of these S-block elements, sodium, potassium, magnesium, and calcium, are just non-negotiable for biology.
Absolutely. The sodium-potassium balance is arguably the single most important chemical process in animal life. Sodium ions are kept outside your cells, and potassium ions are kept inside.
And that imbalance, that concentration gradient, is what lets your nerves fire.
It creates the electrical potential across the cell membrane. The sodium-potassium pump works constantly to maintain that gradient. It powers every thought you have, every move you make.
Then you have magnesium, the power broker.
That's a good way to put it. It's a mandatory cofactor for every single enzyme that uses ATP to release energy. No magnesium, no energy from your food.
And in the plant world, its role is even more central.
It is. Magnesium is the metal ion at the absolute heart of the chlorophyll molecule. The entire structure that captures sunlight is built around that one magnesium atom.
And calcium, of course. We know it's for bones. There's about 1,200 grams of it in the average adult.
Right. It builds the static structures.
Yeah.
But it's also a dynamic signal. It's vital for incredibly fast processes, like mediating muscle contraction and initiating blood clotting.
Which brings us to a more chilling example of these periodic trends. The Chernobyl disaster.
It's a stark example. When radioactive strontium-90 was released, its danger came entirely from its spot on the periodic table.
It's right below calcium in group 2.
Exactly. So the body's uptake mechanisms can't really tell the difference between them.
So it absorbs the strontium.
And incorporates it directly into your bones and teeth, right where the calcium should go. It continuously emits radiation, leading to bone cancer. It's a terrifying but also elegant demonstration of why these chemical similarities matter so much.
Okay, let's shift gears to some chemistry we encounter every day. The industrial side of these compounds, like washing soda.
Right, washing soda. Sodium carbonate decahydrate. It's made on a massive scale using the solvay process.
Which is all about exploiting solubility, right?
It's very clever, yes. You start with cheap materials, limestone and brine, and use ammonia. The key step is that sodium bicarbonate is not very soluble under the right conditions.
So it precipitates out.
It crashes out of the solution, you filter it off, heat it, and you get your sodium carbonate. It's essential for water softening, detergents, glass making.
Then there's the simple but vital chemistry of lime. Quicklime and slaked lime.
Quicklime is just calcium oxide, Texbay. You make it by heating limestone in a huge kiln. But when you add water to it, it reacts violently, gives off a lot of heat.
That's slaking.
That's the process of slaking, yes.
Mm-hmm.
And you get calcium hydroxide or slaked lime.
And depending on how much water you add, you get different things.
Correct. A clear solution is lime water, famous for turning milky with TeXKO222. A thick suspension is milk of lime, which is used in sugar purification and to make bleaching powder.
And finally, the material that's inside almost every modern building, gypsum and plaster of Paris.
Gypsum, or calcium sulfate dihydrate, is a soft mineral. Its real value is its incredibly low thermal conductivity.
Perfect for drywalls.
Perfect for drywalls. But the real chemical magic happens when you heat it just right.
To 393 Kelvin specifically.
Precisely. That gives you plaster of Paris, or POP, calcium sulfate hemihydrate. If you go too hot, you get dead burnt plaster, and it won't work anymore.
And its killer feature, its key property, is that it sets with water.
Right. That's what makes it so revolutionary for everything from casts to construction.
So why does it do that?
Because when you mix the hemihydrate powder with water, it rapidly rehydrates. It recrystallizes back into the full dihydrate, back into gypsum. And this process happens in about 5 to 15 minutes, and it expands just slightly as it hardens, forming a solid, rigid structure.
Perfect for immobilizing a broken bone.
A perfect example of controlled crystallization being used for, life-saving purposes.
What an incredible journey. We started with this simple idea that these elements just want to lose their electrons, and that one desire explains, well, everything.
From nerve impulses to airplane parts.
To why a cast hardens around your arm. The trends in atomic size and ionization energy really are the narrative backbone of this entire deep dive.
And we saw how the little guys, lithium and beryllium, stand apart. Their tiny sizes and high polarizing power force them away from simple ionic rules and more toward covalent behavior.
Which opens up unique reactions and applications.
It does.
And that concept, polarizing power, is where we want to leave you today, with a final provocative thought.
We learned beryllium forms covalent compounds because of its high polarizing power. Okay. Now, consider lithium iodide. Text-line alide, it should be ionic.
But it's not, is it?
It shows significant covalent character. And it's soluble in organic solvents. That runs completely counter to the general rule.
So here's a question for you. We know that small, highly charged cations like TeXli plus dollar have high polarizing power. But the iodide ion is one of the largest, softest anions there is.
So what specific combination of atomic properties, thinking about that extreme size difference between the tiny TeXli plus khaki cation and the huge TeX-barion, causes the usually ionic lithium to mimic beryllium's covalent tendency in this one specific compound?
Think about how a small, powerful magnet might distort a very large soft cloud. Some food for thought until our next deep dive. Thanks for tuning in.